And as usual, I'll review the previous lecture. And if there are any questions that come up, please do ask. So, all right. So what we talked about last couple of times, well, actually throughout the semester, we've seen that internal symmetries play an important role in constructing healthy quantum field theories in 2+1 and 3+1 dimensions. So here by healthy, I mean UV well-behaved. UV well-behaved, do you guys recall what it meant? It meant that deep in the UV, the theory doesn't have irrelevant deformations, right? So it's controlled. And how did symmetry help us? It helped us by controlling the terms that were generated throughout the normalization group flow, right? So it was more tame because terms had to respect the symmetries. So the examples that we constructed in 2+1 dimensions have a lot of real-world applications. The one that we discussed in detail was the ON model. That was a Wilson-Fisher fixed point that was reachable within perturbation theory at large N. This was a conformal fixed point in the infrared. N equal 1, this is a 2+1 Ising model, which is used in magnetic moments in thin film. N equal 2, this is the XY model. It's used for superconductor films and Josephson junction arrays. These are applications in real-world applications. N equal 3 is a so-called Heisenberg model that is related to phase transitions that ferromagnets or antiferromagnets undergo in thin films. Thin films because we were talking about 2+1 dimensional physics. But the main point for us was that we wanted a theory in 3+1 dimensions. And we saw that scalar field theory was not well-behaved. But the first example of a sensible 3+1 dimensional theory that we encountered was Yang-Mills non-abelian gauge theory. Example would be, for example, QCD. We calculated the beta function. We saw that if you don't have if you don't have too many fermions, right, the presence of the abelian gauge field gives you anti-screening. Fermions give you screening. If you don't have too many fermions, anti-screening wins. The theory is asymptotically free, so it's sensible in the UV. But the most important thing for us as like if you want to use quantum field theory as for fundamental physics is the so-called Sander-Woolley particle physics that we're going to discuss today. So that's the triumph. That's the biggest achievement of this formulation for fundamental physics. We also discussed spontaneous symmetry breaking of gauge theories. We talked about how it's used to model superconductivity, Cooper pairs. We talked about, and then the key idea over there. I promise you that it's going to play an important role in Sander model. But the key idea we saw that was that a gauge theory is long range. When you have a condensate of a scalar, in the case of in the superconductivity, it's a fermion pair. You end up with a gauge boson that's massive. That makes the force short range. We talked about if you start with a massive vector field, that's UV, the UV properties of that is bad, right? So this was a phenomenologically reasonable way of constructing a model with massive vector fields, massive gauge bosons, that's UV good. But hopefully you recall that the UV behavior is really of relevance for fundamental physics. As an effective field theory, the theory could be non-normalizable or whatever. That's perfectly fine, right? That's in the same paradigm of Landau. All right, any questions from this part? Just quickly reviewing. So last time, what we talked about was anomalies. Anomaly is a classical symmetry that does not become quantum. So this is important because we use extensively symmetries to construct quantum field theories. So from Q51, you recall that from Noether theorem, we learned that continuous symmetries give us conserved currents, right? So if you have a conserved current, is a vector field, J mu. This is conservation law, and if you integrate, so J0 is charge density. If you integrate on this is time, on a codimension 1 surface, you're going to obtain charge, right? Now, if this is some initial time Ti, this is some final time Tf. Integrating this equation between Ti and Tf in this d-dimensional object gives you Q at time F minus Q at time I, because this is 0, the difference has to be 0, therefore charge is conserved. So does this, the question is, in the quantum world, does this promote does this get promoted to an operator equation? And anomaly is precisely the case that we have a classical symmetry that does not survive in the quantum case. To build intuition about anomalies, we talked about massless spinors in 1+1 dimensions. But to tell you in advance, because today we're going to talk about a Sano model, this is going to be important because in Sano model, we're going to have chiral fermions. And this is a consistency of a quantum field theory with chiral fermions. So the simplest example was massless spinors in 1+1 dimensions. So 1+1 is so easy that you could work out everything explicitly in one slide. We went over this last time. This is the Dirac algebra. The Pauli matrices are basically what generate the representation theory of Lorentz Poincare group for you. Gamma 5 is this 1 - 1 operator. It's just, you use it to construct the left-handed and right-handed chiral modes, right? But in 1+1 dimensions, this is literally, as we saw from Dirac equation, these are left-moving and right-moving particles, right? We talked about that last time. Here's the Dirac Lagrangian for massless modes. It splits into right movers and left movers and right movers. This is a minus sign here. Now, what is the theory of chiral fermions? The theory of chiral fermion is wanting to have only this degree of freedom and not this guy, or perhaps treating this guy and this guy differently. In the case of Sano model, what we're going to do is we're going to have one of these guys be charged under some gauge group and the other guy be charge neutral. So if we want to give them different charges, that's like treating them as independent degrees of freedom. All right, so we did calculate the charge and the chiral anomaly, but we started with an intuition that was based on the Dirac C, right? So because this theory, these are complex fields, right? So there's a rotation by phase, chi plus chi minus, going to e to the power of I alpha plus minus x chi plus minus. This is a U1 symmetry. There are two independent U1 symmetry that the conservation law for which would be charge densities conserved for plus and minus separately. We talked about the vector conservation, which is the sum of the two, and the axial one, which was the difference between the two. So in the Dirac C, we discussed this last time. We view these chiral fermions as these are left movers and right movers. These modes are filled, right? This is energy momentum, Dirac C, right? And I'm just drawing them discrete because it's easier to draw them discrete, right? So in the vacuum, these guys are filled, these guys are filled, these are half infinite. An excitation of the left movers or right movers, if I can get my left and right correct, is to introduce a hole here and move it up here, right? And similarly, for the opposite chirality, this would be a hole here and an excitation here. But axial charge, which says that the number, that the charge density on the left minus right is conserved, forbids this, to remove left movers and turn it into right mover. That should be forbidden. And that should definitely be forbidden for a theory that's only made out of left-handed particles, left movers, right? For genuinely chiral theory, that must be forbidden. All right, so we introduced a background electric field for these fermions to make them charge. We don't even need to do quantization or anything fancy of the background electric field. It's just a background field. We put them in some background electric field, and we saw that what happened was that, well, the right movers, their momentum increase, and the left movers, depending on the charge, right, the momentum decrease. And in the language of this energy versus momentum plot, it looks like introducing the electric field basically introduce a bunch of holes here and added a bunch of particles here. That breaks the chiral symmetry, at least now the axial symmetry, right? Now, this was just like intuition building. Then we talked about, we went over the calculation using the Fujikawa method. So this is the infinitesimal, plus or minus, the infinitesimal transformation is like this for the vector and the axial one. I mean, particularly, I've used this, you'll notice that I've used some sort of like an intelligent representation that I've written psi and psi bar for the vector and axial in a similar way, but moved gamma 5 on the right side, So that's a trick. So the conservation, this is a classical symmetry, because under this transformation, the Dirac action changes by this much. This is a total derivative. You do integration by parts, assuming that your boundary is all the way at infinity, as we usually do in flat space quantum field theory. You drop this term, del mu of phi is 0, right? So this is a classical symmetry in the absence of a boundary, or a boundary all the way out at infinity. This keep in mind, because we're going to come back to that. But this classical symmetry, how could a classical symmetry not become quantum? Well, what was quantum mechanics? It was a path integral. Here is an action. The action played the role of the measure, right? So the only way that it could fail is that this integration variable, these integration measures, are not invariant, right? This is precisely, we give the example we just discussed, is precisely the reason that you could not put a chiral fermion on a lattice. Because if you could put a chiral fermion on a lattice, it would mean that you have introduced a regulator for this guy that preserves chirality. So this is impossible. We went through the calculation of this. I'll not repeat that again. What we saw was that, well, okay, let me say quickly. To perform these path integrals, we wrote the path integrals in terms of the eigenfunctions of the Dirac operator, right? And you're integrating over these eigenfunctions. Then to perform the integral, you have to introduce a Jacobian. We calculate that Jacobian. That Jacobian was the thing that gave us the anomaly and the inconsistency. So we calculate this. This is the so-called axial anomaly. Axial anomaly means that this classically is correct, but once you put an operator, there will be something sitting here. All right. A theory with chiral fermions that are charged under gauge transformation must have zero chiral anomaly, or it's nonsense. So we'll see that once we introduce standard model particle physics, an important check of sanity check is that chiral anomaly is canceled. All right, so this is a review of the last lecture. Any questions? Yeah.
So the Higgs mechanism gives mass to fermions.
Yeah.
Right. And that
to the vector field.
And then that term breaks chiral symmetry explicitly.
Well, we'll get there. We'll talk about the electric weak within the standard model. But finish your thought.
But that doesn't have anything to do with the APJ anomaly.
Okay. That's a very loaded question. We'll go through that and we'll discuss it. It will be next lecture, actually. Electric weak symmetry breaking. Let me see. Can I say something this? Yeah, let's say, so ABJ anomaly, I mentioned it last time, just in words. ABJ anomaly is usually referred to the anomaly that you get in this 1 + 1 dimensional case. If you consider 4-dimensional fermions, that's usually the context of ABJ anomaly. There's a triangle diagram, Feynman diagram, we're going to draw and calculate, and we'll discuss that. But do ask your question. All right, any other questions? Very good. Does anyone have an answer for that? Fujikawa actually in the original paper addressed this, but yeah.
Is it a failure in the Hamiltonian constraints?
No, it's not that fancy. So the calculation we just did, that's a beautiful question. The calculation we just did is free fermions, right? We could do canonical quantization for free fermions. We did that in like part 1 QFT, right? So what goes wrong? All right, so I wasn't going to comment on this. I'm just going to give you a hint, and then you can go and read about it. What happens is that, so remember when we said we had a symmetry, it was represented by Wigner's theorem. It was represented as a unitary or anti-unitary in the Hilbert space. So now this is no longer a symmetry. It turns out that if you go through why symmetries, genuine quantum symmetries represented as a unitary, what you find here is that when you have an anomaly, your transformation is no longer a unitary transformation. You pick up phases. So it's an operator that looks like a unitary, but it's not fully unitary. So there's a long story behind that. Even the original Fujikawa paper is readable. You could just pick it up and read it because they work out free fermions. It's almost this question is almost never discussed in textbooks, but yeah. Another way of saying that in some simple examples, in the case of chiral anomaly is a little bit different, but it has to do with I'll tell you more about it. It's about index. Any other questions? This is an important point because we're going to switch gears, right? If you have any questions to ask, because what we're going to do for the next 4 lectures is going to be Sanom model, which is going to be one particular quantum field theory, which is very, very important for particle physics, for fundamental physics. All the examples of quantum field theories we constructed so far were useful for condensed matter, right? We didn't have any good model that was used for particle physics. And this is going to be our holy grail. We're going to be beating this theory up. All right? Okay. I will be coming back to axial anomaly when we talked about anomaly cancellation within Sanom model, and that's lecture 4 of Sanom. But for now, we're going to switch gears. Okay. So what is Sanom model of particle physics? It's a 3+1 dimensional. Now you guys are in QFT2. I can say these words. It's a 3+1 dimensional non-abelian gauge theory coupled to matter. It's a model that unifies all forces and known particles, at least known until recently, except for gravity, right? And it plays a role similar to the role that, so this is Sanom model, the particle content of Sanom model in one plot. It plays a role that in the 20th century of the atomic table, the periodic table in the 19th century. You know, the atomic theory in the 19th century, or late 19th century, early 20th century, convinced people that the whole diversity that we could see in material, it all comes from just atoms. It's all emergent phenomena, right? All low energy effective theories. Now, you need a formalism that will explain this emergent phenomena starting from this building blocks. What is that formalism? It was quantum mechanics and statistical physics, mostly statistical physics. Now, the analogy here is that in the 20th century, we have particle physics, right? We have all sorts of different forces and all sorts of particles, especially with hadrons, things that are charged under a strong force. There's a zoo of these particles. And quantum field theory plays the role of the atomic theory. And the formalism that explains how these emergent phenomena come about is the normalization group that we discussed extensively in this course. All right. This is a high level picture. Questions? We're gonna get into this. All right. So it's a non-abelian gauge theory plus matter. Let's start with the gauge content. So there will be. So first, I'm gonna split down the matter content into the gauge field content and the Higgs sector. You know those words now. It's a renormalizable interacting 4-dimensional quantum field theory. It describes a strong nuclear force. So it's a gauge theory. What's a gauge group? SU3C, C for color, SU2L, L for left-handed, times U1Y, Y for hypercharge. Okay, so this is a gauge group. This is not this. People put this Y to remind yourself that this is not the U1 of electromagnetism. This is a gauge group you start with. These two guys together are called electroweak. They describe the electromagnetism plus weak force. And then this is a strong nuclear force. Of course, gravity is not in the picture. So this is SU3 gauge theory. The gauge bosons are gluons, right? Adjoint representation of SU2 has how many degrees of freedom? 8, right? There are 8 generators. SU2 left, there are 3 generators. These are all spin 1 particles, right? In gauge theory, the generator was spin 1. And then there's one spin 1 that's the generator of this U1 hypercharge. We're going to call it B mu. So just notation, A, the index is I'm using for SU2 runs from 1 to 3. These are the adjoints of SU2, which were, what are the generators of the adjoints of SU2? Paulis, yeah, half Paulis. And these guys are, I'm going to tell you about them today, but you already have worked them out in your homework, Gell-Mann matrices. All right, C is for color. These are called gluons. So here, L means that it's coupled only to left-handed fermions. This is the first sign of chirality. We're going to talk about this. So if this is the case, we're gauging chiral fermions. We must check whether we have chiral anomaly. If there's chiral anomaly, the theory should be thrown into garbage. So this is hypercharge. It's not the electric charge. All right. Questions about the gauge field, the gauge group? We're going to see it's renormalizable, which means what? Beta function is beta function. So it's asymptotically free. That's important. And it's important because like QED on its own was sick, right? There was a Landau pole. More importantly, there's no chiral anomaly.
That's what you mean with pure QED doesn't exist.
Yeah, pure QED doesn't exist. Well, every theory, it's not just it's not just renormalizability. Renormalizability is like like poor man's way of checking things. You have to calculate beta functions, and if you find the Landau pole, as a good physicist, you take this as an indication that there are new particles you haven't discovered yet. So you ask the government to build a larger collider, right? That means that we've discussed this many times, right? If you see hints of non-renormalizability, it's telling you that there's a particle to be discovered soon at higher energies. Your effective field theory is breaking down. It's in the same paradigm as Landau. Make sense?
You stick at one loop.
Yeah, the one loop already is telling you that there's something sick about it. Does that make sense, right? So extrapolating the one loop answer to deduce a Landau pole is not really okay, like rigorously, but higher loops are not going to help you make this turn around, right? As long as the beta functions are analytic functions, that's definitely going to be the case. Any other questions? No, okay, so I'll tell you more about this offline. So this is the gauge content. Now, besides the gauge fields, we have leptons and hadrons. These are the fermions of the theory. So we have one Higgs field, which is a complex scalar field, and we have leptons and hadrons. So here's the definition. Leptons and hadrons are all fermions. So leptons are those fermions that are not interacting through the strong force. Which means that they're charge neutral under SU3 color, which means that they transform in one trivial of SU3. All right. How many of them are there? There are 6 of them. There is electron, muon, and tau, and electron neutrino, muon neutrino, and tau neutrino. 6 of them. We collectively write them as L. Because they don't interact through SU3, through color, the Feynman diagrams we draw, you could recycle the same calculation of electron for tau by changing the masses, right? Now, here comes one important point. I'll try to repeat this a million times so that you guys don't get confused. We're dealing with a theory which has chiral fermions. I'm going to review the representation theory of the Poincare group quickly for you guys to remember what chirality was. But if you recall from QFT1, we went through this. There is the chiral notation and Majorana notation, right? If you have a chiral mode, it's your choice. It's a convention. And in this course, I'll be following Majorana convention. One little warning, Srednicki and Peskin use chiral notation. For other reasons, I can tell you why. A lot of particle physics textbooks actually use pure Sanomol textbooks use Majorana notation, but it's a choice. All right, so I'll review that now. Oh, actually, before saying that, so these are the leptons, 6 leptons. We also have hadrons. So this is terminology. Hadrons are particles that do participate in strong interactions. Now, we're not talking about all hadrons. We're talking about elementary particles of hadrons, the fermions that make up all of these, right? Because we said that before QCD was discovered, we had a zoo of hadrons. And QCD allowed us to tame this zoo and describe everything in terms of SU3 color gauge theory and 6 quarks. So down, strong, bottom, and up, charm, and top. There are 6 of them that we collectively use Q because the Feynman diagrams are again very similar. The masses are different. I'll go over it. I'll go over that. All right, so let's try to organize these nicely. Here are leptons and here are hadrons. We could organize them into 3 generations. So instead of neutrino electron, neutron muon, neutron tau, I can write this neutrino M. M is the generation index that runs 1, 2, 3. Electron, muon, tau, EM. Think of muon as like a second electron, and tau as the third electron. And similarly for up and down, UM and down, DM quarks. Right? We'll see that this way of thinking about stuff is important. There are 3 generations, a fundamental property, is a fundamental thing that's built in the standard model. We're gonna at some point discuss why 3. Could it have been 4? That's a very important question. We're gonna maybe comment on physics beyond standard model at the end of one of the lectures. All right. Any questions about the matter content? So leptons, hadrons, and the gauge content. Any questions? So to describe these, what should I give you? To describe these particles, you guys.
Mass and spin.
Mass and spin, which is representation theory of Poincare group, but also should give you the representation theory of the gauge groups, which is their charges. Right? So if I'm describing a lepton or any of these particles, I'm going to give you a triplet, 3 numbers. This is going to be the SU3 color representation, which for leptons, what am I going to write here? What? Trivial representation. Charge, right? Now, here is going to be SU2 left, and here is going to be the U1 for this notation. And the masses and the charges, masses and spins, but spin I already told you what they are, right? All the gauge bosons spin 1, you knew that. All the fermions I'm describing, they're spin half. There will be 1 spin 0 particle called Higgs, right? That's going to play an important role for us because we see massive vector fields through spontaneous image breaking. Questions? Oh, actually, yeah. So, any questions? Just to make sure that you guys don't get confused, because I used to get confused all the time, I'm going to review the Majorana versus Wild, right? And I'll tell you what is the cost of introducing Majoranas. It seems it's a little bit more work, but I'll clarify all of that. So if you have any questions, do ask. All right, so a quick review, a 2-slide review of spinners in 3+1 dimensional that we went through in QFT1. So what are we dealing with? We're dealing with Dirac spinners. What was a Dirac spinner? It was a 4-component spinner, complex, right? So this is how we organize it. How did we build representation theory of Poincare group? Lorentz group. Mass and spin. How did we do it? What was the starting point? I just did in 2D. Dirac algebra, right? So we solved. I did not derive it this way in QFT1, but the afterthought was that it's actually through construction of these objects, right? Okay, so here's the representation theory of Lorentz group. These fields under, so first of all, Lorentz transformations or Poincare Lorentz transformations are going to be represented as unitaries on the Hilbert space, on the Fock space, right? And here's how they transform. This is the Lorentz transformation acting on it, and this is the matrix that acts on it. This is a 4x4 matrix, representation matrix, right? This has nothing to do with four-dimensionality space-time. It's related through representation theory. All right, so what are these matrices? These are exponential of I over 2, W or omega mu nu, J mu nus. J mu nus are the generators of Lorentz transformation that you could use them using epsilon tensor to construct J's and K's. These K's are boost and J's are rotations, right? Now you should recall that the way that we constructed these in terms of these block diagonal matrices was through the Dirac algebra, exponentiating the solutions to Dirac algebra. This already tells you that if you don't have masses, you could organize this four-dimensional vector in terms of a pair of two components. This is the chiral basis. We call it chiral basis because this representation is block diagonal, right? It's 2x2, 2x2, 0, zeros, right? So if you don't have a mass term, at least not at this level, the chiral things transform under, what was the transformation? What was the representation theory we wrote? We wrote half 0 and 0 half bar, right? I don't recall, did I use this notation or 1 0? Half, yeah, that's what the chart is. All right, because this is reducible, right? Because it's reducible. So this is all classical physics. We said in QFT1, this was like an important thing I said a million times, a particle in quantum field theory is an irreducible representation. So this is a pair of, it's reducible, it's made out of a pair of irreducible representations. It's a direct sum of a pair, which means that you have two particles. So if you want a chiral particle, that will be an irrep. Good? But notice that this is a basis, right? These matrices, I'm just writing in this basis that's block diagonal. I could pick another basis. This we call the chiral basis, right? So now let's talk about these two component fermions. The gamma 5 operator that we defined through the Dirac algebra is identity minus identity in the chiral basis. 1 plus gamma 5 divided by 2 and 1 minus gamma 5 divided by 2 is the projection to the left chirality, left chiral mode, right chiral mode, right? It just gives you this matrix. Zero versus 0 identity. Right? All right. Good. This is the left-handed Weil spinor. This is the right-handed Weil spinor. Now we said, so now I'm going to get to Majorana's. We said that if chi is a left-handed spinor, and this is the epsilon tensor, I sigma 2, epsilon psi left, or sorry, if psi left is a left-handed spinor, psi left star is a two vector acted by this tensor thing, transforms as a right-handed spinor. We did that on the board, right? We derived this. So as a choice of basis, I can represent this one degree of freedom in the following way. So this is the upper one, and then the lower one is basically epsilon star of the top one. This is called the Majorana basis, right? It's when the antiparticle is present, it's just the same as the original one. You're just constructing it by hand, right? But it's just a representation theory. This is a basis. It's a choice. That's why it's a choice. I could, like a matrix that's like 1 0 0 0. After rotation, I can write it differently. It's the same concept. Now this is a Majorana basis, and for the left-handed, so we also saw that if chi is a right-handed, minus epsilon chi star acts like a left-handed. So we're going to describe the same pair of left-handed, right-handed degrees of freedom in terms of Majoranas, right? It seems like I'm duplicating my work, but it's helpful. So again, we're describing Sana model and the Majorana spinor notation. All right, questions? Question about Maranas and Weil and all of that.
Why didn't you Chiral formations? Why
Oh.
didn't you-
Okay. So you see, it's a little bit like the atomic theory was assumed that all material is made of atoms. Now there is atomic theory and there's quantum mechanics and statistical mechanics, but then there's a particular model, which is the periodic table. It's the model that you could use, somebody came up with it, and you could use to describe the claim as it could describe everything. Standard model is a particular quantum field theory. People wrote down a particular matter content that the claim is it could describe everything. Why? Because it works. If tomorrow you could find a simpler model that would work, everybody would switch. You won't, but be my guest. All right, any other questions? The standard model does have problems, by the way. We're not done with particle physics, right? Even before gravity, it has problems. We're going to talk about that. But the problems are not foundational. It's not like as a quantum field theory is sick. It has problems, subtle problems matching nature out there, which is good, which means that there's a window towards new physics beyond standard model physics, right? You guys know an example of that? You know.
Neutrinos and mass.
Yeah, neutrino masses, neutrino oscillation, neutrino masses, right? We'll talk about that one. Anything else actually?
The Higgs self-interaction.
The what?
The Higgs.
Self-interaction. There are some fundamental problems like what you just discussed, and then there are certain things that are just ugly about it. You would like to have a better description. Like for example, we have a lot of things that are fine-tuning. So regarding the self-interaction, I'll talk about this. It seems like Higgs is fine-tuned. The whole theory is fine-tuned. Fine-tuned means what? Means what? That I'm outside this room, I walk in and I see a pencil standing on its tip. That checks with all laws of physics, but you raise an eyebrow. Why? It has to be extremely fine-tuned. So Higgs is very, very fine-tuned. We'll talk about that. That's not an inconsistency, but what you're talking about is something we have to describe. We need something. We're going to talk about this. All right. Everything is good with Majorana versus Weil. If you do get confused, do ask, because it took me a long time to get used to Majorana notation. All right. Now, let's start with an electron. So an electron is a Dirac fermion. So I'm gonna use the word left-handed and right-handed because it's a pair of degrees of freedom. But the left-handed, I'm gonna use it in Majorana notation for it, and the right-handed, I'm gonna use a Majorana notation for it. Good. So it's like this. I have 2 degrees of freedom. This guy, and what I'm gonna call, so this is my psi. What I'm gonna call psi left is going to be this Majorana mode, which is not psi left, but it's made out of it. It's a basis. It's the same. It's a basis I'm using. And then what I'm going to call psi right is going to be chi minus epsilon chi star. Right? Good. Now, an important part. I said that. I said that I have SU2 left. Let's take it as example electron. So electron will be made out of 2 parts. This is the left-handed electron, and this is the right-handed electron. Only this guy is charged under SU2 left. That's first sign of chirality of the theory, right? I'm going to give them different charges if you wish. One of them has charge 0, the other one has non-trivial charge. Now, it's SU2, which means that it's going to transform in what? It's going to transform as a fundamental. I need a pair. So electron left moving, electron is 1. What's the other guy? No, the positron is this, the Majorana piece of it. It's not even the positron, it's the whatever we write down there. It has to transform as a two-dimensional, because the representation theory of SU2 fundamental is two-dimensional complex vectors. I have to have something to put here. So this is, I have to have something else. It sits with the neutrino. That's why we put the index of generations. Right? So the left-handed electron, which was E1, sits in the same doublet, SU2 left doublet, with the left-handed neutrino 1 neutrino electron. That's why we call neutrino electron. Tau and mu, similarly, they sit next to their corresponding neutrinos, right? But the right-handed guys are not coupled at all to SU2, right? Good. So okay. In this representation theory language, I'm talking about the lepton. So I'm gonna put a 1 here. I have to put SU2 left. If I have a fundamental of SU2 left, which is in this P left neutrino, P left electron left, P left electron left, right? What is this? 2, yeah. All right, and similarly for the hadrons, for my quarks, I'm going to put fundamental represent. They're going to be transferring the fundamental, which is 3, and anti-fundamental is 3 bar, right? And the trivial representation is 1. So everyone's good with the representation theory of it? There's a lot of representation theory going on. Not all two-component vectors are created equal, right? We have the spinor vectors, 2 vectors. You have the SU2 doublets vectors. So you got to keep track of these. Questions? But you see the point of the generation, right? Because it's like we have 3 copies of the same SU2 left. The Lorentz representation, the Poincare representation theory is different, right? Which part of it is different? Spin is half, and masses are different.
This left choice that it was chosen to be left, it's completely within language. It's a pronoun language. We might as well have chosen just SU right and left, and that's it.
Yes, okay. Yes. Yeah. You're asking, yeah, this left chirality, yeah, that's right. It's representation theory of Poincare group. There are 2 modes, and you pick a chiral basis, you give them different names, right? How did we switch left and right? We talked about the symmetry and go back to QFT1. We talked about it. So initially giving them labels of left and right is a choice. But once you fix them, you could ask the following question. What if I change all the particles at one moment in time? Do my physical laws change? That's a question of CPT, right? Parity, charge, and time translation. Do go and look at, because we won't have much time to talk about the CPT here. Yeah, I think it's in the extra lectures on the website. There's a, so there's like up to 30, lecture 33, or the non-perturbative business. There's a lecture which is about the this term. The axion term. In that lecture, I talk about CP because it's relevant. It's CP violation, right? So over there, I review it. I might actually, well, we'll see. I might have a comment about this somewhere in the next lecture. So I might squeeze something. All right. Any other questions? All right. So to help us a little bit more, well, I still have to give you the hypercharge. So hypercharge is about how these fermions transform under the U1, right? U1 is a billion. Its representation theory is how many dimensional? 1 dimensional. It's labeled by single number charge, right? All right, so here are the leptons. I have neutrino M right? Neutrino 1, neutrino 2, neutrino 3, aka neutrino electron, neutrino mu, and neutrino tau. Only left-handed. There are no right-handed neutrinos, period. Okay? I'm just not going to include them. Now, electron, there are left-handed and right-handed modes. But when I say electron, I mean the whole three generations, electron, muon, tau, and EMs, right? Here's a notation. Curly E is going to be left-handed lepton, and capital E like that is going to be right-handed, right? And then this is that every time I write mu, unless I particularly say I'm talking about beyond standard physics, it's neutrino, it's always left-handed, right? So that's my notation. Now, my hadrons, which are quarks, right? Left-handed, I use this Caroline notation, U of M. These are, again, Majoranas, right? And they're corresponding right-handed guys. So each of these guys have two Majoranas, right? D similarly. Good? So Caroline means left-handed. Caroline interacts through SU2 left. Capital letter doesn't. It's right-handed. Good? There will not be a right-handed Majorana neutrino. If you introduce such a field, it will have to transform in with what representation? 1, 1, 0. 1, why? Because it's a lepton. The first one is because it's lepton. It must be lepton. Then it has to be 1 because it's right-handed. It can be charged under SU2. And for many phenomenological reasons, you don't want it to have hypercharge either. So it will have to transform this way. This guy, if you introduce it, is going to hard to embed it into the model because it's not interacting with any of these guys. It does not interact through the gauge fields, right? So phenomenologically, it's going to be very constrained, corner in a corner, right? There are reasons to think about this. It's not nonsense for beyond standard model physics. I might have a comment about this, but this is, you need to have 1, 1, 0. All right.
You wouldn't be able to observe them to detect them, please.
Well, we'll talk about this. The fact that we have neutrino masses tells you that there's something wrong with what I'm saying. But I'm telling you the narrative of standard model as it was created. Yeah. We'll talk about that. So actually, you have a homework problem in which you introduce a right-handed neutrino and look into it. Yeah, you have a homework problem that's exactly about that. There's a really nice textbook, standard model. That's where I learned standard model from. It's by Guy D. Moore and someone else. I absolutely recommend that textbook. A combination of these introduction to standard model, one of those words. But this guy, Guy D. Moore. All right. He goes on and they go on and on talking about, and Cliff Burgess actually. The other guy is Cliff Burgess. They go on and on talking about the right-hand neutrino. All right, any other questions? I think you have a homework problem on this. All right, now it's time for giving you the representation and charges. So here are the leptons and here are the quarks. All right, left-handed, now I just put them just with the generation M, right? Because they transform the same way. PLM, right? These are left-handed leptons, right? Sitting this way as a doublet. This is the neutrino, and this is this electron, 3 generations. It transforms as a 1 because it's a lepton, as a 2 because I wrote it so. It's fundamental, minus half. That's its hypercharge. Minus half hypercharge. Okay. Right-handed is 1, 1, minus 1. 1 because it's lepton, 1 because it doesn't interact through electroweak, and doesn't interact through SU2 left. Minus 1 is the hypercharge. These are just numbers I'm giving you. The same way that I told you that somebody came up with the periodic table, somebody came up with these numbers, and it works pretty well. At this point, it's just the data that defines the theory, right? We said that if you want to define a theory, you give me the representation theory of it. The moment you say gauge fields, you have to give me these numbers. These are the quantum numbers of my reps. All right. So here's our right-handed leptons. Now, left-handed quarks, the up and down, curly up and down, sit in a doublet, hence the name up and down. They transform under 3 fundamental, 2 fundamental of left, charge, hypercharge 6. All right. Now, there's a right-handed up quarks and right-handed down quarks that do not sit in a doublet. I just have to treat them differently. And here are the reps. 3, 1, 3, 1, plus 2/3 minus 1/3. So at this point, I'm just inventing these numbers. Because I'm describing to you the same way that somebody describes to you the periodic table. Right? This is just facts. Take them as for granted. And then there's like 60, 70 years of data that is described using this stuff. A lot more than that, actually. All right. Any questions about the matter content, the gauge content, and the leptons so far? There's one particle that remains. What's that one? Higgs. No, before talking about Higgs, okay. Before talking about Higgs, I want to say, remind you of the Majorana notation and its consequences. So this is a left-handed. Majorana means that there are these guys have their antiparticles. So here they are. There is P right of LMs that transform as 1, 2, half. So the hypercharge is the only thing that changes. Do we check that actually why that's the case? Then P left of E of M, the hypercharge is the only thing that changes. Now, when it gets to quarks, the hypercharges are flipped, but also these quarks, the right-handed, the antiparticles of them, they transform in the anti-fundamental. So this is the cost that you have to pay. You have to keep track of these guys as well. But you could always write the left the while part, and this part is just copy it. Just there are a bunch of rules that you copy. We'll see it. Every equation I write, I keep track of these guys for reasons that will come clear later. All right. So now I've actually described the whole. Well, this part was liquid. You knew from the representation theory it had to be these. These are fixed. The data that I have to give you is really already in this page. In the chiral basis, this page doesn't exist. Right? It's a choice of basis that I use. All right. Any questions about the hadrons and leptons, quarks and leptons, and the gauge fields? Yeah.
There's nothing with your priority that constrains the value of the hypercharge.
Does anyone want to tackle this question? A priori, no. But do you have a yeah? They end up being your electromagnetic child, but you're gonna see they play a very, very important role. These numbers are not only the right numbers that will match your phenomenology, electroreceive, interbreaking, all of that. These are the numbers that exactly will give you vanishing chiral anomaly. When we calculate chiral anomaly, these numbers are multiplied by a whole bunch of things, a bunch of negatives and positives, and the results should come out as 0, or standard model belongs to garbage. These numbers get it right. Well, we'll do that calculation. It's pretty cool. It's a very cool calculation. A bunch of numbers like this, they all add up nicely and work out to give you 0.
So just out of curiosity, the fact that there are 3 generations, does it have anything to do with the fundamental?
No.
Of anything?
No. That's just a matter content. I'm just telling you that like previously I was saying I had one scalar field. I have to take 3 copies of it with these prescribed masses. Just like it's what describes nature. Now the why 3, I think it's an open question. There is no explanation, fundamental explanation. It's a little bit, there are some afterthoughts, meaning that if there were more generations, then phenomenology will get messed up, right? So there are those kind of afterthoughts, but as At this level, it's just a fact about, like, again, periodic table. Somebody drew this table for you. Any other questions? All right, so what's the representation theory of our gauge bosons? The gluon is 8, 1, 0. 8 means what? Adjoint. 1 means, it means that there is no vertex. Well, there's the generator is not charged under SU2. That's sensible. The group is SU3 times SU2. That times says that they can't be talking. And then 0 hypercharge is also times U1. So these are obvious, right? W, mu of A, these are the 3 generators of the 3 gauge bosons, massless gauge bosons of SU2, 1, 3, 0, and Bu is 1, 1, 0. Why 0? Yes, U1 is not, a photon doesn't have a charge. Perfect. All right. Now, what's the Higgs field? It's a complex scalar field that transforms. All I have to tell you is that what representation transforms in. 1 means that it's doesn't talk through a strong force. So there won't be a vertex that connects the Higgs to a gluon. 2 means what? Means fundamental under SU2, right? Minus a half. Hypercharge. Now, I had to make these 2 and minus 1. Why? Well, I had to make these non-zero. Or it had to be charged. Why? Because I want spontaneous symmetry breaking. Remember, the whole point of spontaneous symmetry breaking, you had a complex scalar that was charged, and then it was condensing. So I have to have non-zero charges here. Now, what is the spontaneous symmetry breaking? I think I had the slides that I removed, but next time we're going to talk about it is SU2 left times U1 Y spontaneously broken to U1 electromagnetism. Right? And the Higgs boson is charged in this, well, this is the SU3 color, right? 2 minus half. Right? This guy gets a VEV, breaks this symmetry down. Symmetry, you know what I mean? Gauge invariance. We talked about this. What is spontaneously broken gauge invariance? There's no symmetry being broken. There's no Goldstone boson, right? It's just a long range force that becomes short range. Superconductivity. Always think of that example. All right, questions? Any questions about the matter content? I'm done with the matter content. This is all that there is to explain everything from fraction of a second after the Big Bang until now. That's a plan. Modulo 1 or 2 experiments here and there. Well, okay. Fraction of a second after the Big Bang minus CMB. That's indirect. That's extremely indirect. There's no smoking on data. Like we're not missing a vertex. At least in colliders, we haven't seen. Questions? Now, this is the thing that's amazing about a sound model is that it's renormalizable. Meaning what? Meaning that it's hard to tweak it. It's hard to mess with it. The fact that it's renormalizable tells you that very likely there are no new particles for a while. Or if there are new particles, you have to hide them. You have to tune their couplings to be very small. It's hard to mess with it. Right? If it were non-renormalizable, it would have been easier to argue for an upgrade to LXC or any other building a new collider. But nobody would have taken particle physics seriously. All right. Any questions? Remember that like this whole course we've been building up towards a sensible 4-dimensional theory. Now that we have one, I'm presenting to you one of them that's going to describe everything, supposedly, except for gravity. All right, so just to now, those are all words. Let's write down explicitly what this gauge content means, just to set the notation because we're going to be doing calculations. What are the gauge transformations? So here's my U1 YU hypercharge thing. Here is quanta, right, as gauge boson, right? B mu is a vector field, spin 1. There's only one of them. It's gauge transformation. I'm going to write as del mu of a function. I'm going to call it omega 1. Good. Just keep track of the gauge transformations. SU2 left is the gauge boson transforms this way. What is this part? Yeah, so these are the structure constants of SU2 in the adjoint representation. This is a covariant derivative, right? Because SU2 has non-abelian gauge theory. Non-abelian groups have non-trivial adjoint representation. Remember, they have ghosts. That's why they were ghosts, right? So we're going to call these guys, they're now labeled, the gauge transformation here are labeled by the adjoint, the generators of the adjoints of SU2. So it runs from 1, 2, 3. I'm going to use ABC for all of those guys. Alpha, beta, gamma are reserved for SU3. Right, that's a notation. Now, omega 2, A are going to be the gauge parameters for SU2 left. SU3 color, so similar thing, you're going to have the structure constants, and this is omega 3 alpha. It's helpful, just don't get things confused with generations. Here also it runs 1, 2, 3, it has nothing to do with that, right? But it's helpful to have a compact notation. Now, SU2 generators in the adjoint representations are, we said they're Pauli matrices. Here are going to be my notation. I'm setting the notation because we're going to be doing explicit calculations next couple of lectures, right? SU3 generators, where I'm going to use the Gell-Mann matrices. This is half of lambda alpha. Alpha runs from 1 to 8, and here are the Gell-Mann matrices. Now, you don't need to memorize these. They're pretty straightforward. First of all, the first 3 of them are the generators of SU2 copied in the top part, right? And then the rest of them, you just take this guy and swap the rows and columns, right? So here are all they are. You're going to end up with one that's completely diagonal, like, well, that's lambda 8. Did you have an SU3 example in your homework? I think you did, yeah. I think I gave you a mean. I don't remember how bad it was. There was an SU. There was one that was a little bit long. But anyway, that was a while ago. All right. So what are the gauge transformation of the fermion? So the gauge transformation of the bosons are clear. What are the gauge transformations of the fermion? So here is the left-handed lepton as a Majorana. Its left-handed part that I'm denoting by PL acting on LM transforms as 1, 2 minus half. 1 means that I don't need to write omega 3 alpha. 2 means what? 2 means omega 2A tau A. This half is set by the representation theory of SU2. Minus half means minus half omega 1. All right, everybody got this part? All right, this part, the right-handed, the antiparticle is trivial. You just write whatever you write. You have to put the star up there. Good. Now the right-handed leptons is left-handed part is 1. Well, actually, let's start with right-handed part. It's 1, 1 minus 1. There are no tau A's, right? And there are no, of course, these are leptons, so there are no generators of the SU3. There are no Gell-Mann matrices. There are no lambda alphas. All that you've got is just omega 1, right? Charge minus 1, and it's because I'm in my round notation, I have to include this dude as well. All right? So these are my gauge transformations, all that there is to it. Do I have the Higgs? Yeah, I have the, well, no, sorry, I have more. Sorry. There's plenty more. Left-handed quarks. Left-handed quarks, delta QM. The left-handed part, the rest is Majorana part. It's 3, 2, 6. 3 means lambda alpha, I over 3 omega 3 alpha, fundamental of SU3. 2 means I over 2 omega 2a tau a, right? SU2 left, transformation. 6 means I over 6 omega 1. 1 over 6 is the charge. Now for the right-handed part, the antiparticle part, here's the representation theory. I'm just writing down explicitly because you're supposed to be doing explicit calculation. So I'm setting my notation, and here's a suggestion. You don't have to stick to this notation, but I recommend it. It'll save you time. I don't know. I like my notation better. All right, right-handed quarks. Right-handed quark, I have a pair of them. Well, I have 2 of each generations, right? They're each of them they're coming 3 generations. No, they're coming 3 generations and I have up and down, right? So the right-handed UM, capital UM, it transforms in 3, 1, 2/3, right? So 2/3 means 2/3 omega 1. This 1 means that there's no tau a and only lambda alpha is a hadron, right? So the rest you can follow the representation theory. Why don't you stare at it and tell me if it makes sense? Questions? The Higgs you can write down there as well. I'm not gonna, it's the simplest one. It's a scalar, right? All right, so I described to you the gauge content, the leptons and hadrons, quarks, and the scalar field. And this is going to be for today. I'm going to review what we went over. And next time, we're going to take this, talk about spontaneous symmetry breaking, the role of Higgs. Then we talk about, there's more to Standard Model. There's more to Standard Model that I have not described. There's CKM matrix. There's a whole bunch of stuff that I have not described yet. We're going to go through that, describe that. But for now, it's just the gauge content that we described, right? The gauge part of it. As we said, Standard Model particle physics describes a strong force, weak force, and electromagnetism. No hope for gravity. It's a non-abelian gauge theory coupled to matter. This is the gauge group. Here are the gauge generators, the gauge vector fields. They're all massless at the moment, right? It must be because it's a gauge invariance. Matter sector is Majorana fermions plus complex scalar field, which is Higgs. Can you, I think you should be able to do this calculation under 5 minutes to look up your notes and calculate the beta function of Standard Model. How would you do it? I just described to you what the matter content is, right? How would you calculate it?
Recycle the calculation.
Yeah, but what was, there were a couple of calculations we did. There was one that was the quickest. Huh? Effective action, background gauge field. So background gauge field effective action, we basically brought this down to it. It was all representation theory, right? You told me what is your matter content. There were a bunch of numbers. You just add and subtract them, and that's your beta function, one loop, right? You can now do that very, very quickly. You see that that's the advantage of all that horrific looking representation theory. Now just tell me like, oh, change Standard Model, but add in this particle. First check that the beta functions are good. All right, then we can talk. All right, fermions. So leptons, they're spin half particles with no color charge. They do not participate in strong interaction. They come in, there are neutrinos and then there are electrons, right? Electron means like the generation electron, muon and tau. And they're neutrinos. I don't think that people say electrons, but you know what that means. EMs. Hadrons, there are particles that do participate in strong interaction. And all the hadrons are bound states of these guys. Quarks and the gluons, or hadron is just any particle, composite or not, that interacts through strong interaction. But the fundamental hadrons are these quarks that we're describing, right? So we organize them into 3 generations this way. Why did we do that? Because of their SU2 left charges. That's why we do that. Good. Then I said that I'm going to describe everything in terms of the Majorana for notation. So their neutrinos are only left-handed, nu m, right? Electron, there will be a left-handed and a right-handed electrons. This is currently this guy, and the left-handed guys sit in a doublet of SU2 left. Those guys go for the right. Hadrons, left-handed, right-handed, left-handed, left-handed, up, down. They sit in a doublet of SU2. A copy of this for 3 generations, for each generation. And here are the charges, right? Good. At this point, these numbers I've just described them. I've given you these numbers, right? All right, so this is a summary of what we're going to go over today. Are there any questions?
It's a silly question, but what type of problems arise if we let right-handed
As I said, either I'll talk about it or there's a homework problem about this. Do you want to answer?
My understanding is that you need to have it be very massive, and then you can use like the seesaw mechanism.
We'll talk about seesaw. So briefly, I give you a hint. The hint is that you have to make sure that it doesn't mess with the rest of the physics. So the goal of introducing a right-hand neutrino is to get the neutrino oscillations to work. But you fix one thing, you don't want to mess up all the other things that are working. So you have to somehow make sure you fix this problem, it doesn't mess up with the other things. So the charges that I suggested, you have to pick those charges, and then there are more consistency checks, right? So it will be tricky to work out. Yeah, good. All right.
Is not the best question, but so if you have neutrino oscillations, there's like a CP violating phase in that. There's also a problem in the standard model, which is variogenesis.
Oh, we'll talk about this. Okay, yeah, but go ahead, continue. Finish your thought.
My question is that the CP violating phase and neutrino oscillations, I think that gives you leptogenesis. Then is the problem really that you just need something that will couple leptons?
Okay, so I'll not actually say much about leptogenesis for the most part because I don't know much about it.
Okay.
I cannot answer your question. I'm not an expert in this, so I don't know this story of like what messes up or not. But I will make some comments on. Well, I won't say much about baryogenesis, but like including right-handed neutrinos, and I'll talk about the masses. There's a lot more in this book by Guy Moore and Cliff Burgess. It's not my field, so I don't know much about the phenomenology.
So from my perspective, there's really three, like you mentioned, there's like beauty problems, right? From my point of view, there's really just three big problems with the standard model: baryogenesis, neutrinos have massive gravity. The rest, I think, are more or less beauty problems.
There is one thing that we'll talk in detail about. Well, it depends who you talk to. A theorist like me is not happy with the hierarchy problem.
Okay, so
yeah, hierarchy problem. It's not a problem
yes.
to say it. It's exactly the same fine tuning. You open the door, there's a pencil standing on it. But we'll discuss that. Come with all the questions for that. Any other questions?
Yeah. Just historically, like I guess the main achievement is coming up with this combination of gauge groups, right? That produces the theory you want. So on the way, was it just trying different combinations of gauge groups? What was that iteration process?
So I do not actually know the history of how this model was written and what are the contenders. I do know the story of QCD. So the QCD I described it, right? There was like, I don't think that, yeah, I did not mention anything about Technicolor. So there were models that people were writing down to describe this zoo of hadrons. That was a big problem in the 60s. And this is a time that, at the time, quantum field theory was not widely accepted as a model of particle physics, right? And that went through many iterations. Like people tried all sorts of things. And then QCD SU3 was crucial. I don't know much about standard model and the history of it. I'm sure if you guys want to read about this and give it journal club, that would be wonderful. But let me tell you a little bit about something, which is, so I said we have a Saddle model unifies all these forces but gravity. I lied. I totally lied because electroweak and this SU2, you need to unify them still, into one force. And that's the story of the so-called general, the gut theories. So that has a larger scale, and people have talked about different models of that. There's SU5, SO10. I know a little bit about phenomenology of that. There was a time that people discussed what the question is, do you have any data that will tell you about whether your gut theories are correct or not, right? And this also, like, there will be a spontaneous symmetry breaking that starts from larger group and breaks it down here, and you got to get everything right. One key issue back over there was that models were suggesting that proton had to decay. And then there was an experiment being built, and it was not conclusive. There's no proton decay observed. So I'll comment on that a little bit as well. Yeah. So there is some guesswork, but there's a whole subfield between experiment and theorists, which is called phenomenologists. These guys, what they do is they live with these models, right? So I'm not an expert on that at all. But yeah. Any other questions? I did not answer that question at all. Sorry.
So this is something.
It's really, I don't know anything about it. But yeah.
It's fine. It's okay if you know. It's related to that. So you talked about grain unification. In that sense, it's like just from looking at it, it looks totally different than this. Sometimes referred to as electroweak unification. Right? Like you have like a greater group like SO10 or SU5, whereas here we still have two separate groups, right? So like, is there really would you think it's proper to say that there's actually a unification, like electroweak unification? For me, I don't necessarily like that word. It feels
okay, so I can say a little bit more about that theories. That's one of the lectures. There's more to it. Okay. It's not just spontaneous symmetry breaking down. Yeah, you want. So yeah, let me not go on a tangent about this. But actually, there's one thought that I want to suggest all of you guys to look at. So the beta functions of one loop or R loops, you could calculate them. At least at low loops is not scheme dependent, and as we learn, very sure of what. So I'm gonna mess this up if I draw it. Let me say the words. So you look at the beta functions and the couplings, right? And some of them are growing, some of them at different rates, right? Beta functions are different. And you look at when two couplings become the same order. That's when two couplings become the same order, that's a hint of a unification. That's the first hint of a unification, right? For example, I don't know, I'm a quantum gravity person, so I'm going to give you a weird example. Quantum gravity, right? So gravity is very, very weak compared to electromagnetic force, right? So gravity plays no role in this room, like in terms of deciding this bound states, right? But gravity, as you go to smaller and smaller scales, gets stronger and stronger. There's a length scale at which it becomes comparable to other forces. That's L Planck. That scale is the moment that you want to unify, right? So there's similarly gut scale. If you look at how the couplings evolve, there will be a scale which is 10 to 16 GeV, around 10 to 16 GeV. That's when you would like to unify these. But again, I'm not a model builder, I'm not a phenomenologist. I don't have a deep understanding of where the gut scale comes from.
I remember in that book, there's actually they don't all three agree, right? You get like a little triangle.
Yeah. So there was a claim of that, but then people argued about this. Yeah, there's a lot of that kind of stuff. Right. But I don't as general field theorists at this point in this course, you guys learned one lesson, right? By calculating higher dimension operators, right? Things that are irrelevant. That's where very, very precisely, that's where you learn about hints of a new physics you haven't discovered yet, right? If you've measured stuff that you were doing very, very precisely, you're trying to rule out higher dimension operators more and more, right? And the constraints that you put on them those are hints for you for how the theory is going to get modified at higher scales. All right, I went over time. Any last questions? If not, thank you so much. Homework 7 is posted due in two weeks. There will be a last one as well for Stata model. Thank you.